In question number 26, a radionuclide A1 with decay constant lambda transforms into radionuclide A2 of decay constant 2 lambda. At initial moment, the sample contains only radionuclide A1 with number of nuclei being N0 at t equal to 0. The time after which the activity of radionuclide A2 reaches its maximum value is given by. So, in order to understand this problem, let this is radionuclide A1 and it is decaying with decay constant lambda 1. It is radionuclide A2 and it is decaying with decay constant lambda 2. So at any time t, at t equal to 0, the number of radioactive nuclide of A1 is N0, and at any time t, let its radioactive number nuclei is N1 and it is N2. Then we know that it is the standard relation that dN2 by dt can be written as lambda 1 into N1 minus lambda 2 into N2. So if I solve this differential equation, then the value of N2 comes out to be lambda 1 N0 divided by lambda 2 minus lambda 1 into e raised to the power minus lambda 1 into t minus of e raised to the power minus lambda 2 into t. So in this question, the value of lambda 1 is lambda and the value of lambda 2 is 2 lambda. So if I substitute this data here, the value of N2 comes out to be N0 into e raised to the power minus lambda into t minus e raised to the power minus 2 lambda into t. Now in the question it is asked the time after which the activity of radionuclide A2 reaches its maximum. So I have to apply the concept of maxima and minima. So dN2 by dt is equal to 0, and we will find that for the maximum the value of t comes out to be ln2 by lambda. So option 1 is the correct answer. Let's move to question number 27. In question number 27, an astronomical telescope has an eyepiece of focal length 5 cm. If the angular magnification in normal adjustment is 5, then the distance between objective and eyepiece, if it is adjusted to give maximum magnification. Since the magnification m is given by f0 by fe, so the value of focal length of the objective is equal to magnification 5 into fe, that is 5 cm. So it comes out to be 25 cm. Now suppose this is the objective lens and this is the eyepiece, and it is given that the focal length of the objective we have calculated, that is 25 cm, and the eyepiece is of 5 cm. We know that the image formed by the objective lens is in the focal plane of the objective lens. So when the rays comes on the objective lens, then it forms an image in the focal plane of the objective lens. So we can say that this separation is 25 cm. Now let this separation for the eyepiece is u. Then for eyepiece we can say that v is equal to minus 20 cm, f is equal to plus 5 cm. So if I apply the lens formula, so 1 upon v minus 1 by u is equal to 1 by f. So if I solve this, the value of u comes out to be minus 4 cm. So we can say that this is 4. So the separation between objective lens and eyepiece is 29 cm. So option 3 is the correct answer. Let's move to question number 28. In question number 28, an energy of 68 electron volt is required to excite a hydrogen-like atom from its second Bohr orbit to third Bohr orbit. If atomic number of atom is Z and energy required to excite from first Bohr orbit to third Bohr orbit is K, then value of K and Z respectively are. So we know that in hydrogen-like atom, the energy difference delta E is given by E0 into Z square into 1 upon N1 square minus 1 upon N2 square, where the value of E0 is 13.6 electron volt. Now in the first case, it is given that the excitation is from second Bohr orbit to third Bohr orbit and the energy required is 68 electron volt. So we can say that 68 is equal to 13.6 into z square into 1 by 4 minus 1 by 9. So if I solve this, the value of z comes out to be 6. And in the second case, delta E required is 13.6 into z, that is 6 square, into excitation is from first Bohr orbit to third Bohr orbit, that is 1 minus 1 by 9. So if I solve this, it comes out to be 435.2 electron volt. So option 4 is the correct answer. Let's move to question number 29. In question number 29, there is a uniform magnetic field B normal to the XY plane. If L-shaped conductor ABC has length AB is equal to 4 meter parallel to x-axis and length BC is equal to 2 meter parallel to y-axis, ABC moves in the XY plane with velocity 8I cap plus kj cap meter per second. If the potential difference across A and C is 0, then speed of conductor ABC is equal to. So the potential difference AB would be 0 when the velocity vector is parallel to L vector or anti-parallel to L vector, because the magnetic field is perpendicular to L vector. So in that case, we can say that the ratio of 8 by k is equal to the ratio of 4 by 2. So if I solve this, the value of k comes out to be 4. So the velocity is given by 8I cap plus 4j cap meter per second, and if I calculate the magnitude of this velocity, then it comes out to be 4 root 5 meter per second. So option 1 is the correct answer. Let's move to question number 30. In question number 30, to cover the area of 1628 km square on the earth, minimum height of transmitting antenna should be, where r is the radius of earth, that is equal to 6400 km. So we know that if r is the radius on the earth covered by the satellite, then we can say that r is equal to under root of 2 into r into h, where r is the radius of the earth and h is the height of the antenna. In the given question, it is given that 1628 is equal to pi into r square. So if I substitute the data here, r square is equal to 2 into r into h, or r square can be replaced from here, that is 1628, it is given in kilometer square, so that is 10 raised to the power 6 meter square divided by pi, and this is equal to 2 into r, that is 6400, kilometer can be written in terms of meter, into h, this is meter. So if I solve this, the value of h comes out to be 40 meter. So option 1 is the correct answer. By this, I wish you all the best for your preparation. Have a good luck.